So we'll start off with a bit of an overview of what organic chemistry is. So according to American Chemical Society, organic chemistry is basically just a study of the structure of properties, properties, composition, reactions, and preparation of compounds which contain carbon. So that including not only hydrocarbons, but also compounds with any number of other elements. So that could be hydrogen, nitrogen, oxygen, halogens, phosphorus, silicon, and sulfur. So basically it's these compounds which have a carbon backbone, and based off this carbon backbone, they then have functional groups which affect the physical and chemical properties and affect what reactions this particular compound can participate in. So we'll look at some general C to H skeletons, so our general basic hydrocarbon chains. And so our general hydrocarbon chains are known as alkanes. And so an alkane means a chain which just has a single bond between any carbon molecules. And so when we look at the naming properties for these, we can see that they have the same general suffix on the end, so that being ane, A-N-E, and then they've just changed the prefix for each of these depending on the number of carbons in the backbone of the molecule. So for example, if there is 1 carbon in the molecule, it will be methane. If there is 2 carbons in the molecule, it then becomes ethane, 3 becomes propane, 4 becomes butane, 5 becomes pentane, 6 becomes hexane, 7 heptane, 8 is octane, 9 is nonane, and 10 is decane. And so what you'll notice about these is that as you delve further into organic chemistry, these prefixes don't just apply to our general basic alkane molecules, but also apply to other molecules such as our alkynes, our alkenes, our alcohols. Just like any organic compound, they'll follow the general same prefix structure depending on the number of carbons in the backbone of the molecule. We can also see, looking back at this, in the far right column, we've got condensed structural formula. And so we can not only draw these as shown in the middle box with the extended structural formula, where it's very spaced out and shows how the molecules are arranged in space. So for example, methane being a singular carbon molecule with 4 hydrogens bonded around it. We can instead show a condensed structural formula where we can write CH4, or like going on to ethane, CH3, CH3. So not entirely condensing it down to its molecular formula, in which ethane would be C2H6, but instead a condensed structural formula where it's showing still the general structure of the molecule in a condensed version, so being CH3, suggesting that there is a carbon molecule with 3 hydrogens bonded to it, connected again to another carbon molecule with 3 hydrogens bonded to it. Next, we can look at some functional groups which we have, and we will delve further into what these are. But just to start off with, we'll just go through a general overview of what these functional groups are and what sort of features make them what they are. So the first one we can see is we've already looked at alkanes, so now we can look at alkenes. So alkenes, very similar to alkanes, except their functional group is a carbon-to-carbon double bond. So this basically means that somewhere along the carbon backbone, there is a double bond between 2 of the carbon atoms anywhere along that carbon molecule. And so an example of this could be ethene, which would be a CH2CH2, and so that would be having 2 carbon molecules with a double bond between them, and then due to the molecule wanting, each atom wanting to have a stable octet, there would then be 2 hydrogens bonded to each of the carbon molecules in order for the carbon molecules and the hydrogen molecules to attain stable octet. The next one we can look at is alkynes. And so alkynes also very similar to the alkanes and alkenes, except they have a triple bond between at least one of the carbons in the carbon backbone. So an example we could have is but2-ine, so that being CH3, C, C, CH3. So what this is suggesting is that we have a carbon molecule which is then bonded to 3 hydrogens and another carbon molecule. And then the second carbon molecule along has a triple bond between the second carbon molecule and the third carbon molecule. So if there is a second carbon molecule and a third carbon molecule with a triple bond between them, we would name it as a but, and then the last one having another carbon on the end with 3 hydrogens bonded to it, we'd name it as but2-ine as opposed to but3-ine, because we want to name the location of this triple bond, so whether the triple bond is located between the first carbon and the second carbon, or the second carbon and the third carbon. If it was between the third carbon and the fourth carbon, we'd just name it as if it was between the first carbon and the second carbon. But we will talk about this a bit more further in depth a bit later. But basically, if it's between the first one and the second one, you'll name it as it being the first one. If it's between the second one and the third one, you'll name it as it being on the second one. And so it's always just about favoring the lowest number for the naming of any organic compound. The next one we can look at is alcohols. So alcohols have what's known as a hydroxyl group. And so a hydroxyl group is composed of an oxygen bonded to a hydrogen. And so this oxygen can be located anywhere along an alkane, alkene, or alkyne chain. And so it will just be this this single bonded oxygen and hydrogen attached anywhere along the carbon chain. And so an example which we could look at could be ethanol. So this being a basic ethane molecule, so 2 carbons. And so normally an ethane molecule would be C2H6, so having 2 carbons and 6 hydrogens. However, one of the hydrogen molecules gets replaced with a hydroxyl group, resulting in ethanol as opposed to ethane. The next one we can look at is aldehydes. So aldehydes have what's known as a carbonyl group. And so a carbonyl group is a double bonded oxygen group. And so in an aldehyde, this is an end chain carbonyl group. And so what this means is the carbonyl group is located on the final carbon of the chain of the molecule. So whether that be an alkane, alkene, or alkyne, the double bonded oxygen or carbonyl group will be located on the last or first carbon of that chain. And so an example of this could be ethanal, so that being an ethane molecule, so a CH3CH3 molecule, except it would then become CH3COH. And this is because we would have the first carbon in the molecule just being this carbon with the 3 hydrogens bonded to it, but then the next carbon along would obviously have a bond to the other carbon, then it would have a double bond to the oxygen, and then to complete its stable octet, it would then need to have a hydrogen bonded. And so because the carbonyl group is located on an end of a chain, so in ethanal, obviously you could only have an aldehyde, it couldn't be located in the middle of the chain. In ethanal, it would be on the end of the chain, and so hence it would be ethanal with the carbonyl group being on the end of the chain. And so we can contrast this with the next one, which is known as ketones. And so ketones are much like aldehydes in that they have the carbonyl group, but the carbonyl group is not an end chain carbonyl group. In this case, it must be a mid-chain carbonyl group. So this means it can be located in any carbon along the carbon chain except for the first one or the last one. So an example we can look at with these is propone. And so propone being a propane molecule with 3 carbons along the carbon chain. The first one and the last one are just a carbon with 3 hydrogens bonded to it, but the middle one obviously is bonded to the 2 carbons on either side of it, but then it's also got the double bonded oxygen attached to it. And so because that carbonyl group is in the middle of the chain, it's known as a ketone, and because it's 3 carbons long, it's propone. And so it wouldn't be an aldehyde because the carbonyl group is on the middle of the chain as opposed to being on the end of the chain. The next one we can see is carboxylic acids. So carboxylic acids have what's known as a carboxyl group. And so what you'll notice about the name of carboxyl is that it sounds a bit like carbonyl and hydroxyl combined. And so that's basically exactly what this is. And so in a carboxylic acid, on the end of a chain, and it will always be on the end of a chain of a molecule, you'll have the end carbon of the carbon backbone double bonded to an oxygen and single bonded to a hydroxyl group. And so this is what's then known as a carboxyl group. So carboxyl group being the carbon double bonded to an oxygen and single bonded to a hydroxyl group. And so these are called carboxylic acids. And so an example of these which we can have is ethanoic acid. So ethanoic acid would be CH3COOH. And so the way this would be set up would be you'd have a carbon with 3 hydrogens bonded to it, and then bonded to another carbon, which would have a double bonded oxygen and a single bonded hydroxyl group. So because it's a general ethane molecule, all single bonds with 2 carbons in it, it's ethane, but then the end of the chain is changed to have a carboxyl group, which makes it an ethanoic acid as opposed to being an ethane molecule. The next one we can look at is halogens. Halogen groups, which can be put onto an alkane chain to make what's known as a haloalkane. And so a haloalkane is quite a simple molecule. It's just the exact same as your general alkane molecule, except one of the hydrogens from the alkane chain has been replaced by a halogen. So any of the halogens from the periodic table, so common ones are generally chlorine and bromine. So an example which we've got here is chloroethane. So in chloroethane, we've taken a basic ethane molecule and we've swapped one of those hydrogens to a chlorine, and so instead of it being CH3CH3, we get ClCH2CH3. And so this could be written a number of ways. It could also be CH2ClCH3. Basically, whichever way it can be written, it's still representing chloroethane because it's suggesting that one of those carbons only has 2 hydrogens and has a chlorine instead. And so with these, if it was longer than 2 carbons long, if it was going into then 3 carbons long, you would need to name the location of the halogen molecule, so of the halogen atom, in order to correctly name the molecules. So for example, if it was a propane molecule and one of the hydrogens on the first carbon or the last carbon was substituted with chlorine, you'd get 1 chloropropane. If it was on the second carbon atom along, then you'd get 2 chloropropane. The next one we can look at is esters. And so what esters are is that they are basically like a combination between a carboxylic acid and another added on alkane chain. So what happens with these is they have part of an alkane chain followed by part of a carboxyl group, so that being a carbon with a double bonded oxygen and then a single bonded oxygen. But then from that single bonded oxygen onwards, they then continue with another carbon chain, being another alkane chain. And so this is what's formed, what's known as an ester. They can also be called alkanoates, and so that's just based off their naming structure. And so, for example, we can look at methyl ethanoate, and so with methyl ethanoate, we'd have CH3, COOCH3, and so that's saying that the methyl group is this first part of the molecule, which is the part of the molecule which is attached after the C double bonded O single bonded O. So it's like the leftover part of the molecule, and then the ethanoate part is sort of what we call like the main chain of the molecule. So this part at the front here, the part which is connected to the carbon with the double bonded oxygen. So for example, if we're looking at methyl ethanoate, methyls being this part on the end here. So if we're looking at this, it would be one carbon over here, and ethanoate is the start of the molecule where we'd have a carbon here and a carbon here. So ethanoate being 2 carbons long, and so that would be with that double bonded oxygen. And so methyl ethanoate would have 2 carbons at the start. The first carbon would have 3 hydrogens bonded to it. The next carbon would have the double bonded oxygen to it, and then a single bonded oxygen in the middle of the chain. And so that forms the ethanoate part. Then from that single bonded oxygen in the middle of the chain, you'd bond a carbon to it and then bond 3 hydrogens to that carbon to form the methyl part of the molecule. The next one we can look at is nitriles. So nitriles have what's known as either a cyano group or a nitrile group, can be called either. And so nitriles are basically just your simple alkane, alkene, alkyne molecules, but instead they've got a triple bonded nitrogen atom on the end of the chain. And so when we look at this, we'd have the chain down one end, and then we just have a triple bonded nitrogen on the end. And so an example of this could be something like ethane nitrile. So we just name it as the ethane molecule because it's got 2 carbons in the chain. And so the first one would be a carbon with 3 hydrogens bonded to it, then bonded to the next carbon, which would have a triple bonded nitrogen to it. And so we can notice with this one, the last carbon on the chain, the one with the triple bonded nitrogen, does not have any hydrogens bonded to it because it's attained its stable octet. It's got 1 bond from the other carbon and 3 bonds from the nitrogen. And so because it needs 4 bonds to achieve its stable octet, that is enough bonds. It's got 1 from the carbon and 3 from the nitrogen. The next one we can see is amines. And so amines have what's known as an amine group. And so this is based off ammonia. And so what happens with these is we can either have 1 R group, 2 R group, or 3 R groups. And so R groups being carbon chains branching off the nitrogen molecule. And so basically what happens with an amine is that you start with the original NH3 molecule, so the ammonia molecule, and each of those hydrogens from the original NH3 molecule can be replaced with carbon chains. So, for example, if we're looking at something like ethylamine, we've only had 1 of the hydrogens from the NH3 molecule replaced by a carbon chain. So we've got a CH3, then CH2, so 2 carbons long, basically along this section here, and then bonded to a nitrogen, and then there'd be a hydrogen bonded here and a hydrogen bonded here. We could also have other options where we can have a carbon chain bonded here, a carbon chain bonded here, and then a hydrogen bonded here, or you could have a carbon chain here, a carbon chain here, and a carbon chain here. So it can be 1, 2, or all of the hydrogens from the original ammonia molecule, which can be replaced with carbon chains, or it can be 2, or it can be only 1. Then building off this, we can go and look at amides. So amides are like a bit of a combination between having a carbonyl group but also having an amine group. And so this is where we can have the carbon, which is bonded closest to the nitrogen, having a double bonded carbonyl group. So we're still basing this off the original ammonia molecule, so an NH3 molecule, and we are successively replacing the hydrogen molecules with carbon chains. However, we can have 1, 2, or 3 of these hydrogens replaced, same with an amine, but one of these chains will have closest to the nitrogen molecule a double bonded oxygen group, so a carbonyl group. And so an example of that which we can look at is ethanamide, so that being having 2 carbons, and then the carbon closest, so if we had a carbon here, and then nitrogen here, the carbon closest to the nitrogen would have a double bonded oxygen, and then we'd have a hydrogen bonded off each of these potential locations for R groups. And then same with amines, we could also have a carbon group based off either of where the other hydrogen groups were located in the original ammonia molecule. So that summarizes all of our functional groups and just gives you